So one of the most prominent algorithms in natural language processing is called Word2Vec. And the goal of Word2Vec is to optimize word embeddings, which you talked about in the intro to the course in the last video. So how are we going to do this? We're going to start by doing this with an algorithm called Word2Vec. And Word2Vec, the goal of this is to create this word embedding so that we can capture the meaning of words with numbers. So how does this work? Well, Word2Vec uses a classic neural network structure with 3 layers. So it has an input, a hidden, and an output layer. But it's used a little differently here because we don't really care so much about the actual outputs of the network. I mean, we need the output in order to calculate our error and thereby optimize our weights. But what are really going to be useful for us are these weights, because these weight values are going to end up being our word embeddings, because that's what we're optimizing when we train a network. Before we look at why that is, let's talk about the Word2Vec model that we're going to be explaining first, and that is the skipgram model. So the theory behind skipgram is as follows. You start with a large collection of words for which you want to derive word embeddings, and this collection of words is called a corpus. So a corpus. This is our a collection of words. And we're going to derive a word embedding, our numerical semantic representation of all of these words. Now your corpus could be any large collection of words, potentially up to many millions or billions of unique words. An example of this could be, say, all of Wikipedia, or a massive collection of tweets. Now what you do with this corpus in skipgram is that you're going to iterate over every single word in the corpus, just like you would, say, read an article going from one word to the next, and we are going to call the current word we are on our center word. Now, as we iterate over each word in our corpus, we're going to define a window around the center word in which we're going to be looking for context words. So let's draw this out. So here's our corpus. This whole sentence here is our entire corpus for this example. Normally, obviously, it'd be a lot bigger, but this is just a small example here. So we'll start by iterating over our words. First, we'll use A as our center word, and we'll define a window. Let's say our window is 3, and we'll call this window value R. So R is equal to 3. That means we're going to look 3 words on either side. So if A is our center word, they'll go 1, 2, 3, and this would be the limit of our window. But let's imagine for a minute that we've iterated over a few words, and now our center word is carry, right here. So this here is our center word. Now, if our window size is 3, we're going to be calling 3 words on each side our context words. So bird could not and a 1 pound. So these are all context words, and each of these is a context word. And the goal of the skipgram model, given this section of our corpus, is to predict the probability of each word occurring given the center word. So if we call the index of our center word T in our corpus, then we need to define a probability distribution for each word occurring at each index, T plus 1, T plus 2, T plus 3, etc. So what does this look like? For bird, this is going to be represented by the probability of T minus 3. So that's our bird word. The probability of that word appearing given, that's what that line means. It means given that our center word at index T has appeared. And that's going to be the same thing for this one, except it's going to be T minus 2. And over here, let's go the probability of the second word on the right side of our window occurring is going to be defined by the probability of T plus 2. So that's this word. We don't know what it is, but the probability of, say, 1 occurring given our center word at index t. So that's the goal of scriptgram, is to define a probability distribution that contains the probability of every word in our window occurring given a center word. And what these are conditional probabilities. If you don't know what that is, that's basically given that something has occurred, what is the probability of something else occurring? I'm writing this out, so if you don't know, you can go look into this a little bit further. But so how are these probabilities determined? Well, this is where our neural network structure comes in. So here's our neural network structure for the skipgram model. Now, it might look a little different from what you're used to, but it's really not. And in code, it's going to look even more similar to what we've gone over in our basic neural network series. But by the way, if you haven't watched, you should go do that before you follow this, because it will be hard to understand. So let's go over the structure here. The input layer here is basically a huge vector that is the length of the number of individual words in our corpus. So that's a lot, and we're going to call this number t. So t equals the number of individual words, or unique words in the corpus. Now, the reason for that is that this input layer is a one-hot encoding. So this is a one-hot encoding. What a one-hot encoding is it's basically a lazy way of representing a word numerically that doesn't convey any meaning at all. That is, the one-hot encodings for two very different words will be exactly as different as two one-hot encodings of words that are practically the same, as long as they are just slightly different. For example, the gerund form of a verb and the infinitive form. The reason for that is that a one-hot encoding is just a really long vector where each position in the vector represents a unique word. Practically all of the vector is zeros, telling you that all of the words that the vector does not represent, except for one spot in the vector, which is a 1, representing the word that corresponds to the vector. So here's an example given our we have 4 unique words in our corpus, and let's say the 4 unique words are let's say the cat is fat. And so we can make a little table here, and then we'll put these also on the top. The cat is fat. And so now let's define one-hot encodings for each of these words. And if you already know what a one-hot encoding is, and this might be redundant, and you can skip this part, but some people may not. I'm trying to cover all the bases here. So the one-hot encoding for the is going to be 4 places long. So it's going to be a kind of here it looks like a vector. It's going to be vector matrix T by 1 matrix. So what's this going to look like? Well, here's the one-hot encoding, and we're going to put a 0 for every word that it doesn't correspond to, and a 1 at the index of the words that it does correspond to. So the definitely corresponds to the. The does not mean cat is or fat. So the one-hot encoding for the is 1000. Now for cat, well, the cat vector does not represent the. It does not represent is, and it does not represent fat. It only represents cat. So the one-hot encoding for cat is 0100. Now you can probably see where this is going, because the is vector should not represent any other words than is. And so basically the word that it represents is only denoted by the index at which the 1 is located. So you can see how this wouldn't convey any meaning, but it is going to be useful for telling us which word we're starting with. So we know that what our input layer is. It's just a one-hot encoding representation of our center word. And that makes sense. In our neural net, we want to know, given a center word, what are the context words most likely to be. So one hot encoding of our center word at the current spot in our iteration, but of our center word. Now our first set of weights, and this one is exciting because it's our first set of word embeddings. So each row in our matrix represents a word embedding for a word in our corpus with t possible unique words, which is the same as the length of the one hot encoding for our current center word, or the number of nodes in our input layer. So that was a lot, but here, this is each row in our, so this is our weight matrix. So this is our weight 1 matrix. And each one of these, this is a word embedding. Each row. So, and it keeps going for t number of rows. And remember, t is a number of individual words in our corpus. The second dimension, which I've called v, is the number of columns in our matrix, or the number of values in each row. And if each row represents a word embedding, then v is the number of values in our word embedding vector. So v is the number of values in our word embedding vectors. We saw in our introductory video, for example, word embeddings for colors had a length of 3, that is R, G, and B. For conventional Word2Vec models, word embeddings usually have a length of about 25 to 1,000. However, and that number is a hyperparameter that we can define in the creation of our network, but that should give us a ballpark idea for V. So you also might commonly hear this first matrix sometimes called the lookup table, because it is where we get the embedding for our center word that we will be using to cross-check all our context words with. Okay, now on to our little hidden layer here. And in this kind of model, you also sometimes hear this referred to as the projection layer, and this is our v by 1 layer here in the middle. But basically what this is the transposed word embedding for our center word that corresponds to our inputted one hot encoding. So this is sometimes called the projection layer. I might refer to that I might refer to it as that in the future. And this is the word embedding transposed for our center word. So that's what this means. The T means transposed. If you don't know what that means, then you should go back and watch some of the basic neural network video series where I explain that. And the center word, it's the center word, and I'm just denoting that with this little subscript center. And the reason that this layer arises so nicely to be that is that when you take the dot product of our input and weight matrices, then nearly everything in our one hot encoding is going to be zeros, because we are multiplying, and because we are multiplying each row in our matrix by 0 and adding them all together, except for the one row which gets multiplied by our solitary 1 from that one hot and added to the rest of our rows, which here so far had just been 0, then the dot product here essentially just selects out the appropriate center word embedding and takes that as our hidden layer. So that's the only real goal of this first section as far as feed-forward operations go, is to select out the center word embedding. So maybe one of these is the center word embedding. And maybe these are all zeros. Maybe we have a 1 in here somewhere. And when you dot product these two, all of these are going to be 0 and so forth, except for this one. And when we add them all together, this becomes just transposed and to our hidden layer here. So that's what this hidden or projection layer is, and you can hopefully see why, is it's just the transposed word embedding for our center word. It gets a little more interesting when we start looking at this next set of weights here. So we'll call these, this is another set of weights. This is weights 2. And really there are quite a few set of weights, but we'll cover that in a second. And the goal of our next section here is to produce a probability distribution of all of our context words given our center word. Before we talk about how we're going to calculate all this, we should talk about what a probability distribution is and why we want one. Basically, what a probability distribution is a list of the probability of each possible event occurring on a scale of 0 to 1. And usually, and at least in our case, all of the decimal values in the probability distribution will add up to 1. For a very simple example, take a coin toss. So this is the probability distribution for a coin toss. The two possible outcomes or events that can occur are that the coin toss could land on heads or it could land on tails. And in an optimal coin toss, both of these events are equally likely to occur. So our probability distribution is 0.5, 0.5, where each position in our probability distribution represents an outcome. So this could be heads, and yes, there's a 50% chance of it being heads, and there's a 50% chance of it being tails. If our coin was skewed, then maybe the head side was weighted, so that it's more likely to land on heads than tails, and maybe our probability distribution could look like 0.75, 0.25. Or in this case, there's a 3 out of 4 times you'll land on heads, and 1 out of 4 times you'll land on tails. So then each of our little output layers, these are each individual output layers of our network. These all output probability distributions of their own, and it's really a matrix where the 1 is the value in our probability distribution from 0 to 1, and t is the number of unique words in the corpus. So what does the probability distribution that our network produces represent? Well, at each location in the window here, we get an output probability distribution that is the same dimensions as our input layer. So that's right. Each of these layers represents a spot in the window. So this could be spot t plus 1. So if our center word index is t, then this could be spot t plus 1, t plus 2, and t plus 3. Now in other example, there would be actually 6 of these layers. I only drew 3 because my screen is only so big. At each location in the window, we get an output probability distribution that is the same dimensions as our input layer, or the number of unique words. And here, each value in the output vector or matrix also represents a word, but really it represents the probabilities for each word of that word occurring given our center word, or our conditional probability. So here at each layer, this is a probability distribution that looks like it's probably a pretty big matrix like this, and each spot in the matrix is only one value from 0 to 1, and each spot here represents a possible context word. So a possible context word. And this will be over and over again, and each of these possible context words is represented by the probability of that context words, and so it's the length of all the individual words. So the possibility of that unique word occurring given our center word. So each of these is a conditional probability of the probability of the context word occurring given our center word. Okay, so how is this conditional probability calculated now? To do this, we are going to use a special kind of new activation function at each of these nodes. Commonly utilized for classification tasks like this one, where you need a bunch of probabilities, and that is the softmax activation function. So let's see what the softmax function looks like. So this is what our softmax function looks like. We'll call it S, so we'll say S of our input is going to be xi. And what xi is, this is a scalar value that is part or of a vector of length k. Part of vector length. Well, yeah, we're just calling this k for this example. So this example could look like this. Here's our input vector, and this would represent our output layer in that neural network model we just showed. And we have, say, x1, x2, x3, and x4. And we're taking for each x value in this vector, we're going to calculate a probability for it. That's what this I represents. So S of xi is going to be equal to e, that's Euler's number, to the x raised to the power of our input over the sum of all the values. It's we'll call this I. No, we already called that I. Just call this k. Sum k. So remember our length k of e to the x at the index k. So what this top part is, this really serves the purpose of makes the output positive. And the bottom is a little more complicated, but it shouldn't be that too hard to understand. Basically, this is the sum of Euler's number raised to each of our x values in our array, our vector over here. So the top, we take our individual x value, raise e to that. The bottom, we say, oh, we're going to take the first one, raise e to that, then add it to the second one or add it to e raised to the second one, then add it to e raised to the third one, and add it to e raised to the fourth one. And this really normalizes the outputs. So that, remember, it can be on a scale of 0 to 1, where the probability of all these adds to 1 on the output. This would be the input, but on the output. So normalizes the output. And remember, the vector of length k, in our case, is going to be one of our output layers, and k is really going to be t, the number of unique words in our corpus. So the final activated output of one of our output nodes, we'll call that xi, is going to be equal to the raw value of that node, xi, divided by, which is going to be the dot product of the hidden layer and the final weights, divided by the sum of e to the value of all your other nodes in that layer. And when you run all the nodes in your layer through this function, then you get a conditional probability distribution for all the nodes, which represent context words in that output layer, which represents a spot in our window given a center word. Great. Hopefully that makes sense. One last thing, though, before we wrap it up, though, I want to talk about why giving xi to our softmax activation function makes sense and kind of where that comes from. Now, I said that xi represents our raw node value before it goes to the activation function, but what is that value? Well, we know, because this is just our regular feed-forward operation in our network here, that our output layer is given by the most recent hidden layer with the dot product of the weights. We already talked about how our hidden layer is just the word embedding for our center word. That's this layer here. That we selected from our lookup table, that's this, using our input one-hot encoding. That's this. And this has the dimensions of v times 1, or v by 1. Now we know what we want our output table to be, a probability distribution of all our context words occurring. But where do these context word values come from? Where they come from our second set of weights here. And these are our word embeddings for our context words. And that is this set of weights. Not to confuse things, but yes, each word does have two word embedding representations. One for when it is the center word, that's here, and one for when it is the context words, and that's here. And really, these are the same weight values, all of these, but it's going to be run multiple times with each each represent window spots in our window. So this having these 3 layers here really just represents an iteration. And also technically these 2 sets of word embeddings do not have to be the same length, because this second V here kind of cancels out during the matrix multiplication, but I called them both V just for simplicity's sake, and really most people just keep them the same, I'm pretty sure. Also in the second one, the dimensions are switched. So when we take the dot product between our projection layer and the second weight matrix, so this is our projection layer, this is our second weights matrix, what happens? Well, each of the nodes in our output layer effectively becomes the dot product of the 2 vectors. One of them is transposed, of course, and that is our projection layer. So we have a vector in here, and a vector in here. But then each node or x1 value becomes our center word embedding matrixly multiplied with the context with that context word's embedding. That corresponds to that node, and that produces a scalar value. So that scalar value is each of these node values. So this is scalar, and that is the dot product of these 2 vectors. Each of these is scalar. Whoops. And where did we see a scalar number before? Well, this is our xi value. And each of these is our length. Well, it's really length t, but we called that k earlier. So we can just substitute. We say the probability of our output word, that would be our context word, given our center word, is going to be equal to e raised to the output dot product with the center word, and that is the word embedding of the center word that we get here, over the sum, and this is really t, of e to the output word, that's our context word, t, we calling this t now, dot product with the center word. So what does this show us? Well, getting the dot product between 2 vectors gives us a very rough approximation of the similarity between the 2 vectors. And once we normalize this to whole context word the whole context word possibility set, our output conditional probability is directly proportional to that similarity which we are training for. Think about that for a minute and try to make sense of it yourself, because that's a pretty important idea. So next video is going to be a little tangential but very important, where we're going to talk about the special way that we're going to calculate the error that corresponds with our softmax activation, which is a whole rabbit hole of its own to go down. And then we'll start to get into the back propagation and how we're going to train this model later on and calculate the gradients for each weight value so that we can then optimize our word embeddings. And this kind of makes sense that we're not going to be using actually the output probabilities here in the end. We're going to be taking these 2 weight matrices here, and we're just going to take them out of our network and put those somewhere else and use those as our word embeddings, and then we can find similarities between them. And these similarities are derived from where these words occur in relation to each other. If 2 words often occur next to similar words, they're often going to mean more similar things. And once we've trained this sufficiently, these word embeddings should be optimized so we can use them like we were using them in the last intro video. So I hope you enjoyed this. I hope you enjoyed this video. I hope you learned something. It's a little bit complicated, but really exciting stuff. I'll see you in the next one.